My name is Swami Gopal Swami. I spent several years in the automotive industry, primarily in the areas of control design and development. And for the last few years, I've been with Texas A&M University working on connected and autonomous vehicles. So before I go on with what I'm going to talk about, let me introduce my colleagues and co-panelists. Dr. Darba is a professor in the Department of Mechanical Engineering, also at Texas A&M, with focus on control theory and applications, including, of course, autonomous vehicles. He has been working on vehicle platooning for over 3 decades and has developed some fundamental results that provide insights into platooning and connected vehicle operations. Dr. Ratnam is an associate professor in mechanical engineering also at Texas A&M University. His research interests include autonomous vehicles, ground and aerial, ground and underwater autonomous vehicles, vision and sensor fusion algorithms. Somebody asked in the last session what kind of education would make sense to be in this space. Just to give you an example of Dr. Ratnam, he has his bachelor's and master's in mechanical engineering, a master's in electrical and computer science, PhD in civil engineering, and his PhD thesis work was on aerospace. Okay, it's a great pleasure for me to be here to introduce the concept that we've been calling. Let me just see how I should. Okay, so the concept that we are calling as infrastructure-enabled autonomy, and the idea is how that leads to autonomy as a service and what the implications could be thereof. We believe it's a new paradigm for autonomous vehicles, and the primary goal would be to accelerate the deployment of autonomy, autonomous transportation. So let me start with this. Why are we working on autonomous vehicles? Many people have already addressed that before, and so I don't want to belabor that point. Yeah, there are tremendous benefits in terms of the potential for number of lives saved, number of crashes that can be reduced, the economic savings, the fuel savings, and so on and so forth. Obviously, great benefits. But we have to look at the fine print. The benefits accrue with a corresponding penetration of autonomous vehicles in the transportation. You need to have 90% penetration to kind of get the fabulous benefits that we see. Let me see if it doesn't work. Okay. The fabulous benefits that we are hoping to get. And remember, for example, in the US alone, we have about 250 million automobiles, both commercial and passenger cars and trucks, on the road today. And the question is, how do we hope to get the kind of penetration that we need to really get the benefit that we're all touting that we will get? And so that's really the thought process behind what I'm going to be talking about today. We talk about the penetration of autonomous vehicles, and let me kind of give a quick rundown of what people have been thinking, and I want to do this by using the famous Gartner hype cycle for emerging technologies to kind of quickly walk through what people have been thinking. In 2011, in the, I don't know if people are familiar with this hype cycle, but essentially it's just talks about the various emerging technologies that are there and the different phases of enchantment and hype about this technology before kind of you go into the trough of disillusionment and finally kind of get into the plateau of actual meaningful deployment. Okay, so the in 2011, autonomous vehicles did not have a space here. 2011, we suddenly started having autonomous vehicles, and as we walk through, you can see that there's a peak of its hype around 2015, and whoa, it started going down on the trough. And in fact, in 2018, I think I don't necessarily agree with that, but it's the autonomous stuff technology was split into 2 parts. for different levels of automation, and one was continuing to be in the hype cycle, while the other one is going down in the trough of disillusionment. So the point is, as I said, we have 250 million vehicles on the road. How do we expect to accelerate the penetration of autonomous vehicles? Because that's the only way we can actually get the benefits that are being touted that we hope to get from autonomous vehicles. So I come from the automotive background, and so I have an acute sense of what it takes to, or I have an acute awareness of the realities of complex code. Because as you can see, mechatronic system, the modern automobile in general is a mechatronic system. The autonomous vehicle is much more of a mechatronic system, and the complexity is all baked into the software that goes into these vehicles. So we have, in a typical modern car, 100 million lines of code. The complexity is humongous. The number of subsystems, number of engineers working on it, number of suppliers involved, the distributed nature of the development. So the complexity is really enormous. And this is just for regular modern cars, not necessarily autonomous vehicles. And if you just look at some of the headlines, you just have to do a Google search. And this I did almost a couple of years back. There have been dramatic failures across the globe in terms of software-related failures. And when you have software failures in mechatronic systems, that is systems that work not only the software that works with mechanical systems and that which has interaction with the human beings, the costs and impact are humongous. So I'm not going to belabor the impact of the complexity, except to say that we need to really think about how soon do we really expect the people to be taking, for us to be seeing 90% penetration, even 10% penetration, 25 million vehicles on the road. I expect that we probably will have 20 to 30,000 vehicles in the next 10 years in a very limited kind of fashion. So here's my explanation. I want to say how to think about this. So if you look at the driving functions that we do today, you can look at the, let me see if I can get a pointer on this. Yeah. Okay, so the typical modern vehicle, you have a drive-by-wire system that is developed by the automotive OEMs. They help you, once you press the gas pedal, it translates that into how much acceleration you need to get, how much braking you need to get, how much steering you need to provide. You have the decision making. Before that, we have the situational awareness. The driver, as you would see what's outside. You look at your dashboard, kind of make an assessment of the situation and do your decision making. And then you use, in order to drive, additional information that comes from outside. So the distribution of the responsibility amongst these functions, and the responsibility really translates to liability to a large extent, is as follows. The automotive OEM takes care of the green box. The human driver takes care of most of the decision making and situational awareness. And you have some excursions from the OEM onto the decision making by providing some supporting ADAS functions, advanced driver assistance systems, such as lane change, obstacle avoidance, and so on. The information comes from third-party players, such as GPS, cloud services, etc. And there are infrastructure providers, infrastructure primarily being information infrastructure providers who would facilitate the transfer of that information to the vehicle to do the driving. And this is a balance of a distribution of responsibility that's evolved over time, and we understand what it is, we are comfortable with it, and this is kind of where we are right now. If we want to move to a new paradigm of completely autonomous vehicles, what this changes to is the following. The automotive OEM really takes responsibility for the entire driving. And this is where I believe there's going to be a big pause in the introduction of autonomous vehicles in a big way. Yeah, we've already seen many accidents, accidents of that nature. If it were to happen for a large company with selling millions of vehicles, it's going to be big liability for them. So I feel that this will provide a lot of big pause, and so at best we will have 20 to 30,000 vehicles, maybe on a leased basis, they're owned by the OEM and provided on a very limited circumstances. And that does not bode well for our goal of 90% penetration. So what is our proposal? Our proposal is to separate this intelligence that's going to be in the needed for autonomy, for autonomous driving, from being only in the vehicle to being separated between the vehicle and the infrastructure. Take advantage of the infrastructure in a very fundamental way, and that would reduce or at least distribute the liability. And that is kind of what we want to propose as a concept, as an additional in parallel development along with the existing approaches for autonomous vehicles. So the idea is that we have the traditional driving that's taken care of by the automotive OEMs that will continue to remain there, but the situational awareness will come from the infrastructure. I say from the infrastructure, I mean primarily from the infrastructure. And the decision making will be done by third-party units that reside between the drive-by-wire system of the vehicle and the situational awareness on the infrastructure to help make the autonomous driving decisions. So the core concept is what I consider as the separation of issues and expertise. The automakers will focus on the drive-by-wire capabilities and make it even more perfect. They can, of course, bring in more advanced driver assistance systems. But then the infrastructure will become smart and start enabling awareness. And when I say smart infrastructure, what we mean by that is that the perception and the contextual awareness will be synthesized using off-board sensing. So you will have roadside units that will have sensors that will generate, that will be looking at, so you essentially have eyes not on eyes on the road, but placed on the infrastructure. They will be looking at the road from above, generating the situational awareness information, sending that wirelessly to the vehicle. And in order to do that, we leverage connectivity. That's there was another question sometime back, which one should we use? Should it be connectivity or should it be autonomous driving? We believe it has to be a combination of both. There has been significant improvements both in connectivity as well as autonomous capabilities in the recent past, and we need to really bring them together. And what this allows us to do, very interestingly, is this allows us to do on-demand automation, and I'll talk about that later on, because that actually suddenly opens up a possibility for funding this infrastructure investment required that would not be otherwise possible. Here is a cartoon that kind of describes our concept vision. So you have the specialized corridors that we will call as the infrastructure-enabled autonomy corridor, IEA corridor. These will have roadside units. They may look like street lights, but in reality, they are multi-sensor smart packs, multiple sensors that can essentially look at your road and generate situational awareness information. And of course, you don't want to collect all the information and send it blindly to the vehicles, but you have edge computing right there on the edge to abstract that information to the minimally required amount of information that can be sent optimally to the vehicle in a wireless fashion. Then that information then comes into the vehicles which have the drive-by-wire capability, the smart connect device inside, which can talk on the one hand to the infrastructure, on the other hand to the vehicle's drive-by-wire system, and use the information to generate autonomous driving capabilities. Once you have that information, it does not have to be used only for autonomous driving. You could imagine a plethora of uses for such information. It could be sent to a bicyclist or a pedestrian on their smartphones or a smartwatch to give them warning signals of what's happening on the roads. You can send it to manually driven vehicles just as diagnostics and information so that they can drive better as humans. So this is the fundamental concept that we have been trying to promote as infrastructure-enabled autonomy. And let me first walk through a few slides that explain how we have been taking this concept at Texas A&M University. So we started by actually having a clarification on the concept by doing a theoretical exploration of the risks using probabilistic characterizations of the faults and risks associated with distributing the intelligence. So we demonstrate that the risk gets distributed according to the based on the proposed redistribution of intelligence, where we assume that there's a clear partitioning of the functional physical interfaces. Dr. Ratnam and I actually co-authored a paper on this, and the paper's reference is right here. So that's kind of laying the theoretical underpinning for why we would want to work on this concept. The next one was our iteration 0 work. This is where we said, okay, let's now do a virtual simulation of this concept to see if we can demonstrate that things could work. So we have simulation of autonomous vehicle with three, some of the students who worked on this are right here actually in this room. We actually have 3 cameras that, 3 roadside units that are simulated, and the vehicle goes through each of these cameras, and the vehicle is able to detect the, a camera system is able to detect these vehicles, localize that, send it wirelessly, and for wireless communication, we use DSRC units. And the reason we use DSRC unit is not because we have a preference for the DSRC over 5G. We are actually communication agnostic, but we were donated 30 DSRC units for free by Denso Corporation. And that's the reason we use that. But the idea was that the fact that we could use the DSRC implies that's actually one of the lower bandwidth communication capabilities, and we have been able to successfully use that to demonstrate our system, and the implication being that if 5G were to come on board and if you adopt 5G, it's just going to be that much more easier to do it. So that's the iteration 0. The iteration 1 was development of a prototype at our Release campus. Is this the same presentation that I sent you? Sorry. Okay, this is, what's the title? Sorry, can I just ask the title of the presentation? I don't see it anywhere here.
The title of it?
Yeah.
It's titled Your Name.
Okay. All right, that's all right. Okay. Okay, so this is our first iteration. And essentially what we have is we have a Release campus. This is old a military Air Force base that we are using. It's got 7+ miles of concrete runways that we use as an innovation proving grounds at Texas A&M. It's called the Release campus. And that's where we did our initial prototyping experiments. You can see that this is a mobile trailer that has a pole sticking on top of it. We have a camera mounted on top of it. We have wires coming down. We have a laptop serving as the edge computer. And this is the autonomous vehicle that we use to evaluate this capability. So that was the first iteration 0. Then the iteration 2. Before that, I want to show a couple of more videos because let me. Yeah, so this is how it looks like. For example, this is the trailer. The camera is somewhere here. There is an edge computer here that communicates to the vehicle wirelessly through DSRC. And you can see from the camera, we can actually track the vehicle and localize the car in terms of the runway and send it to this vehicle. Yeah, this is what I want to show. This is Texan research, so we have to have the hat. But so this is our very first experiment where we were just doing simple lane changes and so on. This is the Release campus that I just mentioned. It's a 2,000 acre sorry, not old, 2,000-acre military air base repurposed for advanced technology research. We have 7+ miles of connected concrete pavement. We have traffic intersections, specialized roadside units, and 5G connectivity is in the plan. And this essentially becomes our smart city environment that we want to work with. So if we look at the IEA development, how it has moved up to now, on the iteration 2, we have built a 450-meter course with 4 roadside units. These are essentially luminaires, street lights, on which we have mounted the cameras. And let me see if I can, yeah. And this is connected through wire to the edge computer at the bottom. We are still using the laptops for now because we are still in the development phase. But the idea is this can be now made to switch between DSRC or 5G or any other communication method. And we have used this for a variety of testing. And that's kind of some of the testing is what you will be seeing later in the presentations also. And so we have 4 of these light units, about 50 meters between each of them. And these are not powered, so we had to actually have generators for each of those when we are doing our experiments. But this kind of is the beautiful landscape that we get to work with. So some recent tests. So this is multiple views. You can see the first camera tracking the vehicle, and then there's a handoff that happens at some point when the vehicle comes into the view of the next camera, and then there's an overlap period, and after the overlap period is over, the second roadside unit takes over, and they are constantly processing the information, localizing the vehicle, sending that information back to the autonomous vehicle. The autonomous vehicle has a multiple set of sensors because it's being used for a variety of research purposes. But for this particular project, they didn't use any of the onboard sensors. So they relied exclusively on the information coming from the infrastructure, because that's kind of what we wanted to demonstrate. So what I want to say is this is a concept, obviously in its really early stages, but we have already been able to show enough progress that we feel compelled that it's now really time to take it to the next stage. So the technical value proposition is that the multiple sensor smart pack, you can get much higher reliable and precise information because you know the ground truth on these roadside units. Yeah, so you know the ground truth, you can have markers on your road, you can have reconciliation between the different roadside units. Within a roadside unit, you can have multiple sensors that are fused with each other. And not only that, you can also have the ability to avoid occlusions. So if you're driving today, if your view is blocked by a vehicle, a truck or whatever other vehicle that might be in front of you, you really cannot do much. And the same thing applies to sensors that you mount on the vehicles. You can only do so much with the sensors that you mount on the vehicles. And this is exactly where sensors with a different vantage point dramatically changes the clarity of your situational awareness. And then the fact that you have increased computational time, you can do much more in terms of understanding what is happening to your traffic. You can spot potholes, you can identify traffic jams, and most importantly, every vehicle will have the same sort of belief states, shared belief state that is common between all the vehicles, so they know how to try to respond to each other. And mind you, I'm talking about a scenario where it is a mixture of manually driven vehicles and the IEA-driven vehicles. Now, this is the interesting part. What this whole concept allows is provides a new paradigm for doing autonomy. Yeah? The deployment model, how exactly are we going to do autonomous vehicles? So my expectation is the following. I would be driving a vehicle that looks like a normal vehicle. I would be driving it in general as I usually do, except when I go to these congested areas that have an IEA corridor. my commute time, for example, that I spend 1 hour every day, that's when I say, no, I will actually want to go to these IEA corridors. The corridor will interrogate me as soon as I enter there. Say, do you want to be driven autonomously? Of course, there has to be a registration process prior to that. Let's assume that's done. So it interrogates, say, hey, do you want to be driven autonomously today? And if I feel like it, I say, yes, I want to go here, and it drives you autonomously. And at that time, because the vehicle is complete control, you can actually go to sleep. And if you're sleeping when you come close to the destination, it'll park you, and you wake up and drive when you're ready to take it. Yeah. And you get charged by the mile. And that's the key point. So because autonomy does not have, I don't want to be driven autonomously every time. I want to be driven autonomously only under some conditions. I value autonomy only under some circumstances, and the value of autonomy for me is different, and therefore, ideally, I would like to pay only for the autonomy when I really need it. I don't want to pay for all my sensors and costs up front. Here is an opportunity where I pay for my autonomy as a service. I pay by the number of miles that I travel autonomously. So this, I think, provides an opportunity for monetization of autonomy, and this certainly allows private infrastructure players to come into this space. Yeah? So because there's going to be tremendous investment costs associated with instrumenting roadside units every 50 to 100 meters with sensors and having connectivity. Yes, of course. But there is also an opportunity to monetize the usage of that. And that's kind of really the opportunity that we want to present and talk about. So it's not only technical value proposition, so there's a value proposition for a large ecosystem. We believe the automotive OEMs will be only happy because they don't have to deal with taking on additional liability while they still remain in the space of autonomous vehicles. Private infrastructure operators, toll booth operators, cell phone operators, cell tower companies, lighting and urban infrastructure companies, a whole slew of companies suddenly get an opportunity to participate in this autonomous ecosystem. Device makers, the people who make the sensors, the people who make the integration of the sensors that go onto the roadside units, opportunities for them. And the application makers. So when you have a smart connect that carries a whole bunch of information, the number of applications that you can have is limited only by your imagination. I believe that there will be a whole slew of people who will be making different types of applications, leveraging the information that comes in while you're driving. And of course, law enforcement, infrastructure maintenance, traffic management, a variety of users can easily be seen. And of course, society at large, because we believe that this would actually accelerate the penetration of autonomous vehicles, at least in specific corridors. So on a corridor by corridor basis, you can dramatically improve the penetration of autonomous vehicles, thereby reaping the quote unquote promised benefits of autonomy. So that's kind of where I want to start. I mean, there are many open research questions, and we don't have anything solved. Yeah, I mean, we have ideas, and we know the problems exist. We are working on them, but really, there's a lot of work still that remains to be done. We have demonstrated the core functionality at Texas A&M, but we want to increase the complexity of the scenarios that we will be demonstrating. We want to increase the scope of the what we're doing. We want to go from 450 meters to a 2-mile loop. People are working on resilience with respect to cyber attacks, to communication failure. There are a variety of opportunities for doing research on pricing models, perhaps elastic auction-based pricing models. Dr. Korok is an expert on that. Then there's government-private industry partnership models that needs to be looked at. There are legal, risk, and regulatory environment implications that need to be discussed. A variety of business models. I'm not going to go through all this. And last but not least, the issue of privacy. How do we ensure that in having thousands of cameras all around the road does not infringe on people's privacy? So I say with that, that I leave, and I'll pass it on to Dr. Ratnam. This is just, yeah. Oh.
Oh, yeah, thank you. I've been a faculty member at Texas A&M for 10 years. So first year at least, when I was I would come to the lecture room, I would start talking, I would go to the board, write equations and all that. So it was an undergraduate class. So after some of the classes, the undergraduate students came to me and said, "Professor, please, you can say whatever you want, just say howdy before you start anything, and we are all good." So I'm going to say howdy and start my presentation. So, okay, I'm going to talk about infrastructure-based advanced driver assist and autonomous systems. We have already heard a lot of presentations about introduction to autonomous vehicles and the IEA concept. I just want to first acknowledge the support by the Safety Transportation Research Center, which is funded by the US Department of Transportation. And also we work closely with researchers from the Texas A&M Transportation Institute, and of course, all these students who are here, Abhishek, Vamsi, and Kenny, who do all the work, we just present, right? I'll just move on to, I think we have heard from the previous presentations at least, that the road infrastructure is going to significantly benefit both advanced driver assist systems, which is what is called as ADAS, and autonomous vehicles. And in particular, I'm going to talk about proof of concept demonstrations of the IEA concept that Dr. Swami was talking about for different applications first. And then I'm going to talk about the need for common standards. So this is something I think Ken earlier in the keynote speech mentioned, that we need common standards for evaluating autonomous vehicle technologies and taking it forward. So that's something I'm going to talk about. I'm going to mainly focus on lane departure warning systems because that's closely related with infrastructure. So before I move on to the actual slides, I want to give you a sort of intro video on all the testing that we do. So we work on a wide variety of problems from platooning, car platooning, truck platooning, lateral control, vision-based control, and many other things. So this is just a summary of what we have done. So here, this is a promo video, and it's all the frames that you see, the car frames that you see, were all taken when the car was in the autonomous mode. I'm not really a fan of this music, but they said it's a wide, audience, so I just said, okay, why not? Anyway, so what I'm going to talk about is two parts. The first part, I'm going to talk about the roadside camera unit, which we have installed on each of the 4 poles that Dr. Swami was talking about, and how we use that information for some of the applications. And then we're going to talk about lane markings, which is an integral part of the lane departure warning systems that at least is available in some of the high-end cars. So first, in fact, just to give you an idea, deep learning algorithms have been used, or at least been significantly developed over the last few years, and you can use them to identify objects on the road, and you can actually use them to also classify objects into cars, emergency vehicles, police vans, and all kinds of pedestrians and all kinds of things, and you can actually sort of tailor the response based on what kind of vehicles you identify. So this is just a short clip of having some of these deep learning algorithms trained on the data sets that we have, and you can actually classify them into emergency vehicles and police vans and all that. Obviously, if it's a human manually driven car, you would see an emergency vehicle and try to yield to that vehicle and stop or take the appropriate action. You can also try to emulate that using an autonomous vehicle, and in fact, that's what we have done here. So this is essentially roadside unit. Here you have two cars in this demonstration. You have the front car, which is an autonomous car, and you have another car that is following, which is an emergency vehicle. So the autonomous car either does not have the sensor to actually know that there is an emergency vehicle behind, or it's just that, just like anything else that you do, you have sensors, but it's just broken, right? It just doesn't work. So in this case, at least what we have is the information from the emergency vehicle is sensed by the camera unit, and then that information is sent back to the autonomous car using the DSRC communication system in real time, and you do the appropriate response. So that's the video here that you're going to see here, and this is all real-time processing. I can go into more details if anyone is interested, but this is for really two vehicles. We also try to do a platoon of vehicles. In fact, we have we have a platoon of 3 cars here. In this demo, actually, we have the front vehicle is autonomous car, the vehicle in the middle is a human-driven car, and the last vehicle, which is basically either it's an emergency vehicle or police van or whatever it is. And here you see that there is no direct line of sight between the autonomous car and the emergency vehicle. And so these are the kind of applications where the infrastructure roadside units, the cameras could really help. So again, the idea, the concept is the same. So the information is, this information is identified by the camera units and then sent back to the autonomous car, which is what is processed in real time. And that's a response that you see here, where essentially the autonomous car comes to the other lane, and of course a manually driven car also parks itself, and you let the emergency vehicle go. Right. So these are some of the kind of things you could do. You could also we have also done that with different test cases. Here we have modeling humans is always the most challenging thing to do, and you obviously don't want to test these kind of things using real humans. So we have these human-like robots which you can manually control. You can get them onto the lane and off the lane and all that. So the concept again is the same. The information is basically sent from the camera back to the car using the DSRC unit, and you can actually pose a lot of problems. And I know that Dr. Swamy is working on different applications on this. So this is just an introduction to what is possible when infrastructure is not involved. I think the point, again, I want to emphasize is that I don't think there is one versus other. I think it has to be collaborative. You need maybe some onboard sensing, because many of the cars that you buy already has its own GPS units. It has IMU sensors, so you can use that information, and you can mix it with what you get from the roadside units and do better things and hopefully improve safety and everything. And that's the point here, right? So it can complement the onboard perception units. The infrastructure can actually provide real-time information that when you don't have line of sight, direct line of sight, and it provides redundancy. And essentially, most of these applications, I'm sure anyone who works on it knows that things fail, and that's the standard. Rule of thumb is that things are going to fail, and how do you accommodate and react to it is what is important. So if you have more sensors and more redundancy, all the better. So anyway, so that's the first part of my talk. The second part is going to concentrate on lane markings, which is really an integral part of the lane departure warning systems. So we have taken huge strides in autonomous vehicles in the past decade, and this is going to continue, and we are going to see deployments of these autonomous vehicles in some sections of or some cities in the United States, and things are going to improve probably in some sections of the highways. But we are not, the autonomous vehicles, at least in my lifetime, I don't see that completely replacing all the human-driven vehicles. And so at least over the next 40 years, you're going to have human-driven vehicles also, and they have to coexist with autonomous vehicles if at all we have any penetration. So which means that, at least my assumption is that as long as there are human-driven vehicles on the road, you're going to have lane markings to guide us, right? So if you look at it in 2000, there was less than 1% of all the vehicles, at least, equipped with advanced driver assist systems. Depending on what study you look at, by 2030, 50% of the vehicles are going to be equipped with advanced driver assist systems. And when I say these driver assist systems, they could be adaptive cruise control, automatic braking, lane departure warning systems. It could be tire pressure monitoring systems, things like that. The lane departure warning system is one of the key features that is proposed. And the main reason why it's proposed is because people think, at least many studies have shown, that it can actually improve safety. Now, this is just a report from one of the projects, I think, funded by US DOT, where they show that the lane departure warning systems can actually save, that can potentially reduce hundreds of thousands of crashes every year, and can save a lot of lives, and there are a lot of statistics around it. And anyway, I don't want to go through all those numbers, but the point here is that yes, there is potential for safety benefits, but these systems are not yet used, and there are combination of reasons why they are not yet used. It could be because of lack of good lane markings. It could be because we don't have good algorithms yet, or it could be a lack of common performance standards for evaluating these algorithms. So if you look at a lane departure warning system, it's actually just, I just want to tell you how complex this problem is, because, this is just one feature that I would say this is a near-term technology that's going to be there in the cars. And maybe now it's in the high-end cars, but in the next 15, 20 years, I'm sure it's going to be there, more prevalent in most of the cars. And you can see how difficult the problem is when you also have to rely on infrastructure. Now, if you look at a lane departure warning system or a lane detection system, it really consists of three parts. You have the software, you have the hardware, and you have the infrastructure. The software is really the algorithms. Hardware, if you use a camera. So cameras, the reason why everyone talks about cameras is because it's cheap. The LiDARs, I think someone talked about $60,000. You can hope, you can pray and hope that things costs come down, but it's going to take time to actually have cars equipped with LiDARs and really good radars, right? Cameras are cheap, and that's the reason why they are integral part of these lane detection systems. And of course, you have the lane markings, which is an integral part of the infrastructure. But you can actually get hundreds and thousands of variants based on what kind of algorithm you pick, what camera you pick, and what kind of lane markings and the infrastructure you have. For example, if you just take off lane markings, they could be made of different types of materials. You can have different striping processes. You could have white followed by black, and you could have white and black just juxtaposed. You could have different payment types. So it doesn't matter how good your lane marking is. If you don't have contrast between your lane markings and the surrounding parts of the road, your departure warning system is not going to find it. So it's a contrast that is very important. And also your lane geometry, your thickness, and everything. You also have different cameras you can pick, and of course the algorithms. Many people have been working on that, and I don't have time. I think I'm almost done, so I have a couple of minutes. But the point here is that we are not at the end of the story, because the performance does not just depend on the algorithm you pick or the sensor you pick or what lane marking you have. It also depends on the environmental conditions. The edge cases, which is going to really determine. It's not the usual normal cases. The normal cases, you can get 90%, 95% accuracy, which may not be good, but it's still better. But it's the edge cases that's going to really determine how good these vehicles are going to be, or how good these systems are going to be. Now, you can have direct sun, street lights that could deteriorate your performance. You could have, this is one of the hard cases. You could have sun and reflection from the wet surface, snow. You could have old markings, construction sites, pavements. So really, I don't think the camera is going to solve all these problems. You're going to have multiple sensors and do sensor fusion and really to solve this problem. But the key point here is that we do not know what the optimum performance we could get out of just these cheap cameras is at this point in time. At least there is a lack of common standard which could help us in keeping track of the different components of the evolution of the different components of the system and how it affects the performance. So that's what really we are working on. We are trying to develop at least an open source platform where we can test the infrastructure side, the algorithms, as well as the hardware and all that. And we are also developing metrics to actually evaluate, rank these systems and do it. Of course, it has benefits to the federal agencies, the US DOTs and the state DOTs, because they can actually answer questions like, do my lane markings in my state actually, are they fit for level 2 operation or level 3 autonomous vehicle operation? So you can answer questions, simple but basic questions like that. Obviously it's useful for infrastructure providers because they can actually test the new materials, and algorithm developers, of course, because you get new sets of data you can work with. Anyway, I'll just stop with this. I'm just already running out of time. But the point here is that you need a systems approach. It's not about just developing algorithms, or it's not about the infrastructure companies just doing their lane marking. It's an overall system. So you have to look at everything and see if how the improvements in each of the parts will affect the entire system. So with that, I'll just stop. Thank you.
Hi. I'm going to depart from the standard howdy. So anyway, I have about 10 minutes, so I'll try to make it crisp and short and also answer some of the questions that were raised earlier. It's in connection with whatever I've been doing. So I'll focus on certain aspects of connectivity and infrastructure. So for me, infrastructure comes through connectivity, through communications. So what I have been doing for 30 years depends primarily, it's mostly based on how information amongst vehicles will help promote safety and mobility. So this is basically what the focus has been on, and I'll talk a little bit about emergency lane change at the end, but I'll take this time to tell you something about one of the questions that was raised about autonomy and connectivity. So my interest in this particular area of autonomous vehicles goes back to my doctoral thesis, which is about developing automatic vehicle following control algorithms in the 90s for the Automated Highway Systems project. So I'm also interested in the overall, not just in developing the technology, but also assessing what the impact is on traffic safety and traffic mobility. So to give you an answer to that question, so if you are looking at adaptive cruise control systems, which I think all of you know, so the minimum time gap that you need to maintain, okay, which again goes back to my thesis, is that it should be at least twice the sum of all the reaction delays that you would have, reaction lags and delays that you have in the system. Otherwise, you would have this slinky type instabilities, accordion type effect, which will cause pileups. So recently, so this roughly translates to, for trucks, it's about 0.6 to 0.7 seconds. So you're looking at a minimum time gap of about 1.4 seconds. But for eco-platooning and other kinds of things, people are interested in a sweet spot about 0.7 seconds, if I'm not mistaken. So to cut down that much with adaptive cruise control systems, it's just not possible. And people have been doing experiments, and especially in the TNO group as well as in the California Path group. They showed that if you had the cooperative adaptive cruise control system, that is, like if you had the information of the vehicle ahead, acceleration information of the vehicle ahead, you can cut down the time headway. So in fact, my recent paper, this is a paper that I'm quoting, it basically shows that you can cut it down by a factor of 2 if I had the vehicle acceleration information of the vehicle ahead. But if I had the information for our vehicles ahead, like let's say 3 vehicles ahead, I can cut down this minimum time gap by a factor of 4. So that means that connectivity does help, and here is where the infrastructure can actually play a significant role. For example, this is under the assumption that you have perfect communication, okay? So vehicle-to-vehicle communication will not help in the imperfect case because it's primarily local, because it's autonomy is based on onboard sensors. But if you have connectivity, you can get it through the infrastructure, what's happening much farther ahead. And that is what is required, and that's the reason, that's the way how we can actually make the benefits quantifiable. So, and the same thing with safety also. I mean, there are a lot of safety studies that one can talk about. I also work on, the infrastructure also plays a significant role in commercial vehicle operations. For example, one of the projects that I'm doing with Safety Center, University Transportation Center, is on developing automatic diagnostic systems for autonomous trucks, and essentially the purpose is to facilitate pre-trip inspections, automate them, and you could also use it for automating enforcement inspections and to make sure that trucks comply with the FMVSS 121 standard. So this is the kind of a thing that we're doing. There is some work that infrastructure can also help in traffic harmonization, some work that I've done recently. And then in this particular work, for lack of time, I'll just basically focus on emergency lane change. So how does infrastructure help in emergency lane change maneuvers? I think as the previous speakers, of both my colleagues here and the Florida speakers have mentioned, that you could get real-time information about about vehicles, obstacles in a time-efficient manner. But more importantly, it's the not just that you require for safety, you'd also require some way to localize your position very effectively. And here is where infrastructure can actually play a significant role. So not only in terms of safety, I also want to mention here, there are the two types of queues that you would have for lane change maneuvers. Here, in the first one, you would have the queue for emergency lane change maneuver comes from the front of the string of vehicles if you have. And in the second case, as my colleague has mentioned, if it's like a ambulance or something, it actually comes from the back of the string. So if you had information about these things much earlier, then you could plan and act accordingly. And in the second case, it's even more important because it could save lives. So that's the reason why it's fairly important. So in the emergency lane change maneuver, essentially it's a maneuver in which you have an obstacle in the road, and the vehicles are basically trying to evade this. And here I've shown a two-lane scenario where the obstacle is in the right lane, and the vehicles are basically trying to move over to the left lane. Okay. The point of this entire exercise is to show that if you did not have the information of the obstacle and there's no communication between vehicles, then the following distance that each vehicle should maintain should be much more than otherwise. The reason is the vehicle behind would be blinded by the vehicle ahead because it will be blocking the obstacle. And there's no, the thing is, you would want the following vehicle to see the obstacle at least at the same location that the preceding vehicle would have seen it. Okay, and this cannot be possible unless you had some sort of communication, or you keep a huge following distance, and that's basically the point of it. So rough calculations will tell you that it should be at least at the conservative end, it should be about 1.8 seconds of time gap that they need to maintain, and that's clearly not acceptable from the mobility point of view. So I think I don't want to talk a whole lot about the experimental facility at Realis because I think you've seen this before. So here what we are doing is we are looking at an emergency lane change maneuver design and a controller design. So the difference between regular lane change maneuvers and emergency lane change maneuvers is that the vehicle, when it makes a lane change maneuver, you cannot make use of the lane markings or any of those things because the trajectory of the vehicle ahead is is designed in real time, and what the following vehicle has is only limited preview information about how much ever it is. So the question is whether you can actually make that design happen and have a controller which actually tracks the path of the vehicle ahead. This is essentially what the problem is. So we simulate it because I'm only dealing with one vehicle from the point of view of safety first, and then after that, probably in the next year or two, we'll do the 2-vehicle and 3-vehicle lane change maneuver demonstration in a similar setting. So in the first run, what you would have is we just had these cones, and then we had the vehicle drive manually. We stored the GPS information, and this GPS information will basically define the trajectory for the second run, which is the autonomous mode. It's as if it's a following vehicle. And what we want to do is we want to track this. And the amount of information that is available to the following vehicle is just a few samples of where it is. That's about all that you have. And you can actually simulate it for multiple vehicles too, because you can store the second vehicle run and then use the first 2 vehicles, and then you can see what happens to the third vehicle. So these are technical details. I'll just skip it. And this is based on the work of my student, which we published which we presented in ECC in Naples. So I have only 1 second left. So I'll just show some demonstrations. What happened? This doesn't work or what? I thought. So this is at 45 miles per hour. I'll just show two videos. This is the aerial view at 45 miles per hour, and the other one will be at 70 miles per hour. So the cones are the ones which are defining what the lane is, that is the double lane change maneuver. This is the in-car view at 45 miles per hour. None of the cones fell away. Okay, this is at 45 miles per hour. So I'll also show you the 70 miles per hour videos, and then I'll stop after that. I'll take any questions. So the drone that we have was not able to keep track of it. So that's why you'll see a block, because this is going too fast. Okay, and this is the last video. This is the other video. This is at 70 miles per hour. So I think I'll just pass the other demo. So thank you, and I'll be glad to take any questions.
Thank you for the interesting presentations. I like the way you emphasize both the opt-in sort of paradigm as well as thinking in systems. A question I had was, so in my Chrysler Pacifica, I have all the latest advanced safety features you described with adaptive cruise control, and I've got Android Auto that's pulling in the data feed from Google with speed limits, congestion, other things. But currently those two systems don't talk to each other, so I'd like to just take the speed limit feed from Google and tell my adaptive cruise control, just go the speed limit that you know is there. Do you see that kind of like system connection emerging in the coming years, or are there different incentives for the OEMs and the data providers that is kind of hindering that, or what do you see as how that might play out? Because then you could have adaptive speed limits if the weather's bad, and that would feed into the adaptive cruise control. How do you see that evolving in the coming years? Thank you.
This is a problem that is considered, this is traffic harmonization. This is what. So this is traffic harmonization problem. That's what people usually refer to, where you have, it's like variables or speed things and different sections of the highway where you advise in the, that's the kind of a thing that is considered in traffic harmonization problem. I think this can be done. It's not, as the question is, how do you set the speed limits on the highway depending on the weather conditions? And there is research that is going on, and there's some preliminary work that that I had done last year with some of my colleagues. So it can be done.
I just want to add one thing. One is the technologically whether it can be done, and that's of course like what Dr. Deba was saying. It's definitely feasible, but the bigger question is, will the OEM trust the data? And if the data is going to come from a completely different source, then the question of trustworthiness of the data becomes an issue. Whereas if there's a prior agreement that with the infrastructure information provider that this information is trustworthy in some sense, then I think it'll happen. Until then, you cannot do it and make people rely on that.
So normally in scholarly work, we begin with a literature review. Now, in this area, this is quite difficult because you've got a lot of players. There are many universities in this country and all over the world that are working on autonomous vehicle problems. There are many technology companies and auto companies working on this. And even governments are working on all these problems. And I think it really would help this presentation if you step back and gave us an overview, really, that this is a cooperative and competitive effort. Because what you've got, it's in the weeds. You're one player. Maybe you'll be around in 10 years, maybe you won't. And I've seen these presentations, and what I've seen is much more sophisticated than what you've got, but they had a lot more time to present it. And my point is it's useful to put this stuff in context. In other words, what is distinctive about what you're doing as compared with the big picture, which everybody is doing? But this is, as I said, this is a global, cooperative, and competitive effort. But at the same time, those features are what are so important to actually giving us optimism that we're going to get these things sooner rather than later. You may not be part of it, but Stanford might be, Ohio State might be, Michigan might be, or no universities at all. That is all driven by the private sector. So I think broader perspectives on really what's involved here, and not just one small thing and one small problem. You mentioned environmental problems. There are tons of companies who've identified and are working on all these problems as we speak. You know, it's not that you can continue to point to things. I mean, everyone's out there doing this, and I think it's important to really get that message across.
I think it's a fair point, but let me explain 2 points, 2 parts to it. Number one, most of the work that's being done is either looking at autonomy by itself, focusing on the ability for autonomous vehicles, or using the infrastructure to provide augmented information, such as in traffic intersections and specific places like that. There has not been work that we know of that is focusing on providing real-time information from the infrastructure that will actually be used to drive the vehicle autonomously without using sensors on board the vehicles. So that's actually, we have done the research and we have not seen any work that does that, number one. Number two, on the point of the environment, the people have recognized that there is an environmental issue. People have been working on different types of snow weather conditions. But what's not happened is taking a systems view and saying we need to have a standardization that will provide a metric that can be used to say, is this lane keep system good? Is this infrastructure that we provide, is the lane marking going to provide adequate support for lane keep assist? Is the camera system going to provide adequate support for lane keep assist? That's the systems level standardization that's not happened. People have been focused on what's important for them. For example, the people who do vision, they're focused on vision algorithms. The people who do the cameras, they are focused on the cameras. But there is not a general purpose effort, and that's understandable. That's kind of what we want to say, and trying to say we would like to have lane keep or lane marking, lane detection standardization, a metric, a reference system that can be used to promote what it means.
I'll just add one more point. At least from my point of view, most of the work that has been done in companies is from the point of view of single vehicle autonomy. That is, you try to have all the sensors on board and try to make your vehicle as safe as possible. I think one of the efforts that we are trying, we didn't have time to present today, but one of the things that we are doing in at Texas A&M is trying to look at safety problems and other issues for a collection of autonomous vehicles when they are connected. So if you have a platoon of vehicles, let's say, driving on the road, and they're all talking with each other, of course, if we have communication, if great communication between the vehicles, it's all good and fine, but what if that doesn't happen? What if there are communication failures? Let's say if you have a collection of 5 vehicles, if there is a communication failure between the first vehicle and the third vehicle and fourth, whatever it is, how does it affect safety and performance? And so I think our effort has been focused on that. Companies try to do that. I don't want to name the companies here. They have tried to develop safety metrics from a single vehicle's perspective. But it's all great, but it would not work in reality. The reason is that if you're just looking at single vehicle and just trying to make that safe, I don't think you will get the efficiency benefits that you desire. So if you want safety and if you want to have the kind of performance that people are talking about, then you need to look at the collection of vehicles, and that's the effort that we are looking at. And I don't think the companies are. Those are all long-term problems, research questions. And companies, they may get into it, but not right now.
Yeah, don't want to jump the queue, but thanks. So Rick Eddies from Cornell Public Policy. And I want to go to a point Professor Gopalswamy, I have it right, is touched on, which is super important in the policy aspect of infrastructure. And that is, you mentioned charging by the mile. And one of the biggest challenges, seems simple, is how you pay for the infrastructure. And currently we pay on basically a per gallon fossil fuel tax on either gasoline or diesel fuel at both the state and federal level to pay, for the vast majority of the roads. But you mentioned charging by the mile, and the state of Oregon is the leader in pilot projects over the past decade to try to make that simple switch from charging per gallon to charging per mile. And it's been a real slog, a real challenge politically to get drivers to accept that, although the state of California is interested in doing that. So here's my question for anyone on the panel. Do you see the advent of autonomous vehicles as facilitating the acceptance, and they call them mileage-based user fees, MBUFs, and away from a per-gallon gas tax, so that people will be more accepting of incorporating what we would think of in utility pricing as a facility charge into the price of a trip, right? So it's been sort of driver resistance to that seemingly simple change, which is super important in the economics of this. Could we see the interaction of autonomous vehicles and the way you pay for the infrastructure as facilitating that improvement?
Yeah, my thinking is yes. And the reason I say that is if I look at toll roads, that's a prime example where for example, in Texas, we have all these, I mean, in fact, a lot of places, we have this auto charging of the tolls. And it's become now so ubiquitous that you start forgetting and then you start not worrying about it too much as long as it seems reasonable. And it is actually, in some ways, based on usage. And so my point is, people would be more comfortable with paying by mile if the process of doing it is very easy and very convenient. If it's seamless for them, they almost don't have to worry about it. Then I think it will be okay. As against if you have to actually pay explicitly for a bill. Yes.
Great, thank you. Well, first of all, I wanted to build off Cliff Winston's question. And I think, first of all, I think it's not true that there are no companies that are working on infrastructure-dependent autonomy. I'm aware of 2 companies that are building their sensors into the infrastructure because their use cases, they want to serve a limited service area of multiple vehicles. So it turns out to be more effective to build the sensors into the infrastructure than building the sensors into each vehicle. So I think, and so I'm aware of 2 companies who are building out that approach in commercial service. And so I think that gets to a larger question is, what is the right mechanism for public-private interaction and particularly private academic interaction? And I think this is what I'd like to turn this into a question. And the question is, what is your mode of interaction with the private sector been over the last 5 years, in which we've seen not just 1, but 2 sea changes in the direction of investment in autonomous vehicles? About 5 years ago, we started to see a massive amount of private sector investment in autonomous vehicles. Brookings put out a report that said about $80 billion had been spent on JVs and M&A in the autonomous vehicle space. And then last year or so, we're seeing increasing consolidation and engagement in the academic sector. So I would hope that the approach around how do you divide problems, which ones are best approached by the public sector and which are best approached by an academic sector and which one are best approached by the private sector has changed. So I'm curious about what you've seen over the last 5 years or so.
It's a pretty complicated question. So let me try to answer that. My thinking is that, first of all, some of the work that's done by private companies, we don't have access to that. All we know is their marketing blurb. So from a literature survey perspective, we will not be able to assess what exactly they are doing. And so that's my answer was more in the context of the universities. So that's number one. Number 2, but on the flip side, there have been companies, you're right. For example, I think Daimler has a parking lot scenario where you actually drive inside a parking lot where there's a whole bunch of sensors embedded in the infrastructure that support that. What we have been working on is the extreme scenario where we are saying, okay, how much can you push it? Can you be completely independent from sensors to be on the vehicle and use almost 90% of the information coming from the infrastructure? That's kind of how we have been trying to position ourselves. In terms of the public-private partnership, it's actually a ongoing thing. For example, we are discussing with some companies, companies which do lighting, for example, who want to get into smart infrastructure, smart cities. They have been willing to support it. In fact, we may even actually have a formal agreement with them to support some of the work. We have had conversations with many other companies, such as 5G companies that want to install 5G because they need a physical infrastructure also, and we have the Release Campus, and so they've been willing to come down and say, okay, we will install 5G. Can you demonstrate use of that in a very meaningful application? So that's something that we are working on. We have talked with automotive OEMs. They have expressed interest, but we have not had a direct conversation, actual work yet. Yeah, that's kind of, yeah.
I just want to make a fundamental comment about basic research and investment in basic research. All of you sitting there, 30 years ago, the investment at Berkeley and other places in intelligent control systems, path planning, computational geometry, the whole path program at Berkeley. So I think we have to very much pay attention to the fact that investment in such basic ideas, risky ideas 30, 40 years ago that took place is now paying off. And you people are talking about just certain aspects of it, but the basic investment was made 30, 40 years ago, and we should try to keep, as a policy matter, in perspective that fact. Because in the present environment, you will see that we are only picking up the fruits, but we are not looking at the roots of the thing. I think we have to pay attention to that fact.
Yeah, in fact, I'm one of the early graduates of the PATH program. So I was there with PATH from 19. That was what my PhD program was on. So it's thanks for pointing that out. People seem to have forgotten the PATH program and its impact.
I also work for PATH, and we work on fundamental problems, and that's where my interests are. Today's presentation is just one slide. I had 15 minutes to talk, so if you give me more time, I can talk about the fundamental problems. I'm not sure how much of the audience I can retain, but I'll be happy to talk about it.
I don't know how much time we have. We don't. Sorry.
Thank you.
Thanks for watching. Be sure to like and subscribe for more videos from Brookings.